Okay, so let's talk a bit about AWS Lambda. And let's start with the history lesson. Back in the old days, when people ran servers, when people ran services on the internet, when the internet was still kind of a new thing, the model was usually you had like some services that would be run on a Unix host. We're talking about Unix. So if you imagine you have a Unix computer, you have you want to provide services. So maybe you provide HTTP or mail or Usenet or Finger or Telnet, a variety of services your server might offer to other people over the internet, over TCP and UDP, basically. The way that this used to work, maybe about 20 years ago or so, is you would run an internet daemon. You would run on your machine a program that was called like inetd, and it would listen on a socket. It would listen on a number of sockets, and then when a request came in, when a connection was established, it would pass that connection off to some program to be handled. So, for example, if you were requesting a web page, request might come in on port 80, and then inetd would have a config file that would say like, port 80, send it to user local bin httpd, which would be like Apache, and it would just kind of connect that connection. It would spawn this process. This process would read in, would communicate, maybe on standard in and standard out or something for the socket. Details aren't really important. And then when, it would serve up the web page, send it back, and then kill the process. So this is pretty simple because you would just have like one daemon running, the inetd, and that would be a process that's running all the time. And they would invoke these other services to handle requests as they came in from the internet. Any of you ever heard of CGI? Like web CGI bin?
No.
Know about that? Maybe you've seen like in a URL like /CGI bin / like, foo dot, I don't know, Perl or something like that. This is how we used to handle web requests. Basically, a web server would serve up static files, so you would have some directory, and it would have a bunch of images, HTML files, whatever. And when a request came in, it would try. So if you wanted to get like /index.html, there would be some directory on the file system, like user share HTTP or whatever, or www actually, whatever. It would try to look for this file in this directory. If it existed, it would send it back. If it didn't, it would send a 404. So we had these static web servers, and they would basically just handle one request at a time. They would look for a file and they would return it. It was hard to do anything fancy like, fill out a form or send some data to the server or run some program in response to user input. That was initially handled by this strategy called CGI. And so on a form, you would have like a web page, and you would have like form method equals post, and then action equals, and then the action would be something like /CGI bin / like, form mail. Like if you wanted to send an email when somebody filled out the form, for example, which was a common thing, it'd be like formmail.pl, it'd be some Perl file. And the way it would work is the web server, so like Apache basically, when it got a request for anything that started with CGI bin, it would still look for a file on the disk, like on the file system. And if it was executable, it would actually execute that program with the input of your form, basically. And then it could return some HTML as a response. So this is kind of how PHP works by default. This is how a lot of the web used to work. You would hit forms and you would submit them, and it would return a new web page. So the scheme didn't work great for scaling because maybe if you're getting, there's a lot of overhead. So maybe this formmail.pl has some dependencies, like we were talking about. It has some startup time, like we were talking about with Lambda a second ago. if you're trying to service thousands of requests a second, this is not an ideal setup because each time we're creating a new process and it's starting from scratch and it's loading up its dependencies. So they came up with a new scheme that was called FastCGI. And there's other things that are similar to it. And the idea there is what most people use today is you have a daemon that's actually your application. So if you have some mail application, you would start up some process, and it would be like mailer.pl, and it would be running like inetd used to do. So instead of inetd that's listening, we actually here listen on some port, doesn't matter, TCP, and then the web server would be listening on port 80. So like Apache would listen on port 80. Clients would request the web server would basically route certain requests. So if you said I want to hit like / post to like send mail or whatever, then the web server would be configured to take all those requests for that path and send them over TCP or over a Unix socket to this daemon. So they would speak over a socket. Now, the advantage of this is that you don't have the startup time. Basically, you start the daemon once and it waits for connections. And requests come in from the web server, and it would basically usually call a function when the request came in, run some code, and then send a response back. But all in the same process. And then the next request that comes in would talk to the same process and the same process over and over. So it stays resident. It's always running. So this is in contrast to the CGI model where you're spawning a new process each time a request comes in. So this model, this is what a lot of people use all over the world. It's very normal these days. So for example, if you're running our test, like your local development Flask environment, for example, that starts up a web server, usually on port 5000. You can send API requests to that. It's a daemon. It's just, well, usually you don't daemonize it. You just run in the foreground, but it's a program. It's a process that's running. It's a server. You communicate with it. This has some advantages. Like we talked about before, another big one is pre-forking. So if you have a lot of dependencies, so let's say we have, we're running some Flask app. This Flask app has, a whole bunch of dependencies on like SQL Alchemy, Flask, obviously, Bodo3, a whole bunch of dependencies. So when you start up this process, it has to load all this code and data into RAM before it can execute our program. It does all these imports. It's very costly. It takes, maybe, I don't know, 50, 100 megs of RAM to start up, maybe more, depending on the size of the application. So if you wanted to process multiple requests, you don't want to copy this whole block of memory, each request. The way it would typically works is when you start up the server that's going to handle your requests from your from your web server. So the web server could be Apache, it could be Nginx, it could be GUnicorn, it could be AWS API Gateway. It doesn't matter. It's sending web requests over here, over some port, doesn't matter, speaking HTTP. And then our server calls, the appropriate Flask route handler function and returns it. You don't want to copy all of this RAM each time for each request. So what you do normally is you import everything. You import all the dependencies before handling any requests. When a request comes in, what it'll do is it'll fork. They'll call system call fork and create a new process that looks exactly the same. It has a copy of this memory. Everything is copied into the new process's address space. It's not, sorry, I shouldn't say copied, it's mapped. And so in this process space, if I say, call SQL Alchemy, some function, it's really pointing to the same place in RAM that this is. It's not duplicating it. And this way we can, each process that we spawn here, it thinks it has its own copy of everything in RAM, but really it's all pointing back to the same place in RAM. It's shared. It's the same memory, the same imported dependencies, all the code, everything just sits in one place physically in RAM, but these different processes have that one location in RAM where it really exists just mapped in. And so we don't need to make a copy of all these libraries each time we handle a request. And by forking, it's also isolated. So if this crashes or whatever, it doesn't really affect the parent. Any questions on this so far? Am I going too fast? Am I making any sense? Wondered what this has to do with Lambda?
What about caching those dependencies? Well, I don't really get the whole concept of forking.
So the idea of the fork is you create a new process that's a duplicate of the current process. So let me see if I can state this another way. If I can make this more clear in some way, if there's something I'm saying that doesn't make sense, stop me. But typically, so if we start up our Flask dev server, for example, or if we're running our Flask app in sort of the traditional way, what we would usually do is we would have, our app. It depends on a bunch of stuff like SQL Alchemy and Marshmallow and Flask and Verkzoid. And this might get put inside of a kind of application container. So typically people use something called gUnicorn. And it's a web server like Nginx or whatever else. HTTP requests come in, and then it calls some function in here, and then it returns HTTP response. Let's say 2 requests come in at the same time. So suppose we're getting 2 simultaneous HTTP requests to our application. If we just have one thread, one process, we can only handle one thing at a time. Now, one strategy is to just multi-thread your application, and that works pretty well in in Python. In some other environments, it's a lot more difficult to make your application multi-threaded. But the standard approach is either multi-threading or multi-processing. So if we want to handle 2 requests at once, that means we need two separate threads of execution. They can either be threads in the same process or they can be in different processes. But basically we want, if the computer has 2 CPUs, we should use 2 CPUs to handle the 2 requests, basically. So again, one way to do that is threading, but if we forget about threading for now, because it doesn't work so easily in most languages, what we do is we create a copy. So when a request comes, so before any requests come in, we load all our dependencies. We load all our application code into some process. When a request comes in, we make a copy. We take this whole chunk of memory, this whole process, everything about it, its file descriptors, I think, everything, and we duplicate it, we clone it, we fork. We create an exact copy which has all the same code, the same stuff in RAM, all mapped in. So this is really pointing here, these segments, all at one central point in RAM, but it looks like each application has its own copy. If you were to say change something in, let's say the Flask module, then in that case, when you write into some shared memory after forking, then it would take all that data and copy it into your address space. And then your address space would have its own modified version, and then it would be separate. And then you would be using twice as much RAM for that memory segment. It's called copy on write. Anyway, the idea here is that each request, if we spawn a new copy of this for each request that comes in, so this guy would go here, this guy would go here, then we can handle multiple requests at once without using a whole bunch of RAM, because really all these dependencies are only live in one place. Does that make sense?
So these are shallow copies.
Yeah, they're copy on write copies. So they're referencing the same physical location in RAM, unless you try to write something to it, in which case it'll actually copy that to a new chunk of RAM. But yeah, they're lightweight copies. Forking is pretty cheap on Linux, so yeah, making a new process for each request that comes in isn't too bad if we're forking.
All clear.
So I wanted to contrast this with Lambda. So some of this stuff applies to Lambda, like we're discussing a little bit. But also, interestingly, this stuff always comes in kind of cycles. So originally, CGIs were cool, or inetd was cool. Like executing a new process when a request comes in is kind of how everybody did things. And then everyone did things by creating these daemons, these servers that run. That's what we were doing in JetBridge a few years ago when we were using Heroku. But now Lambda's kind of come back to this model of having somebody else run the server for you, and you just kind of saying like, here's when a request comes in, just kind of like run this and give the results back. But you don't really need to leave much running as a daemon. You don't need like a server process. So Lambda, best way to think about it, the way I think about it is it's a API, it's a service. All of Amazon's services are APIs. That's how you interact with them. That's all they really boil down to. And Lambda is an API where it has methods where you can say like, take some code and just save it somewhere with some configuration and a runtime. And then there's another API request you can do that says, invoke this code and give me the result. Like call this function and return a result. That's pretty much what Lambda is. It's an API that lets you store functions and run them. The store function is called, I think, create function or something. And maybe we can take a look at this in the documentation. So we say, okay, I want to store like some function here. Maybe it's a Python 3.8 runtime. Maybe I give it 256 megs of RAM and a timeout of like 10 minutes. And then when I want to call it, I call invoke. And I can send it some parameters. And it calls the function, and then the function returns a result. That's Lambda. Let's take a look maybe at the API. Yes, API Lambda. Whoop. So here's the API reference. We can see exactly how to talk to Lambda here. Yeah, so there's create function. So this describes exactly how creating a function works and what all the parameters are and how to do it. So you provide it, some code. You can tell it what to do if it fails to run your application, if there's an error. Give it a description, environment variables, name the function, a handler, something for encryption, layers, memory size, all this stuff. And then when you want to invoke it, you call invoke or invoke asynchronous if you want. And this basically, you just give it a function. So this, by the way, shows you what the request looks like. And it's just a REST API, like everything else in Amazon. You tell it the name of the function you want to invoke. You give it a payload if you want some context. You can do it asynchronously if you want. And that's pretty much it. So there's a lot of ways to do this. Because it's an API, there's different interfaces. So one thing you may or may not be familiar with is this interface. This is the Amazon Web Console. It's a good way to kind of visually see how stuff works, but it's definitely not the only way to interact with Amazon. So you can use the command line API. So you can say like AWS Lambda, list functions. And there's our functions. So this is exactly the same thing as what we're looking at here in the web. This is just doing a call to list functions, and it's displaying the same data that we see here. I like to use AWS shell too. It's the exact same thing, just kind of in a shell. So you can say like Lambda list functions. And it's got autocomplete. Same stuff. So let's go ahead and make like a simple Lambda. How about we start there? So can create a function. We can just, call it like hello demo. Pick a runtime. So these are runtimes that are supported by Amazon. You don't have to use these things. You can create your own custom runtime. The Lambda environment, let's talk about that in a minute. But let's go ahead and say, okay, I want Python 3.8, for example. And then we need to give it permission. We need to give it an execution role. So the execution role, whenever you run anything in Amazon, you have to give it a role that it's basically that it's its identity. So if usually our Lambdas need some basic permissions. One of the main ones is logs. We want to be able to see what our Lambda is doing in the logs, in CloudWatch logs. So you want to give it permission for that. So say we want to make a role. If we want to make a Lambda, we need a role. So we can go ahead and create a Lambda role like this. Boom, boom. And then we can define it ourselves, or we can use the basic execution role, this guy. What does this do? We can see here, it allows us to put logs to CloudWatch. That's it. So we need that if we want logs. So we'll call it like demo lambda role. And we can see that lambda.amazonaws.com is a trusted entity. So that means we allow Lambda to assume this role. All the Amazon services, they aren't special. They don't have necessarily permission to do anything on their own. They're either using your permissions when you call them, or they assume some role. So we create this role, and we're going to tell Lambda to assume that role when it's executing this function. Demo Lambda role. Cool. So here is our function. So you can see it here. Lambda function, Lambda handler. So the handler here, this is how this works, depends on your runtime. But basically this for Python is a Python package and then name a function in that package. So our package is called Lambda function. As you can see, we have Lambda function.py and then Lambda handler. So we could call this hello, and this would be like .hello. So what'll happen when this function is invoked is Amazon will say, hey, do I have any micro VMs laying around to execute this? If I don't, then I'll start one up. If I start one up, then I'm going to import this. Well, actually, it'll import the whole thing, but it'll have the effect of importing everything in this file. So if I was to say, say like invoke count equals 0, what we could do is we could say here invoke count plus equals 1, and then return hello from Lambda. Let's actually do this. Let's say invocation count invoke count. So we'll return some JSON there. So when it imports this file, this code, because it's executed on import, this will actually be run when Lambda is starting up a new micro VM for us. Now the micro VMs, that's a whole nother tangent. We could go into, it's something called Firecracker. We can discuss that later, but it's a very, 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 very lightweight virtual machine. It's kind of like a container on steroids, but it's something in between a container and a virtual machine, basically, that's running it. The details of what's running our application doesn't matter. We don't care. It's just kind of interesting. It's kind of nice to know about, but it's may change. It has changed. It will change in the future. It shouldn't really be something that we need to care about. But yeah, it is pretty interesting to read about Firecracker. It's their Amazon's micro VM using Linux KVM used for Lambda and Fargate, I think. Anyway, going off on a tangent here, the idea is that this code will be executed when our application starts up. And that includes, let's say I say import, pprint, for example. This will be imported upon when our environment is being set up. Our Lambda execution environment is being imported. So anything in here, anything outside of this function will contribute to the startup time of our Lambda. So if it has to start up a new one because the old one went to sleep, like it got killed because it was idle for 15 minutes or whatever, however long, then this code will be run again. But if I invoke this Lambda several times, I would expect to see invoke count go up because we're reusing the same execution environment. This is only executed once, but it's just calling the function each invocation. But let's find out. Let's try it. See if I'm right. Okay, so we have our function. We have our code saved. We can execute it in the console. We can do like this, but that's boring. Let's execute it with a command line. It's not too hard. So we can say lambda invoke, and then we have to give it a function name. And our function name is hello demo. And we have to give it a name of a file to write the output to. So I'll just call it like res. Okay, and it errored. So I wonder why it errored. Right, let's try it in the browser and see. Syntax error at import.
Can you import pprint?
Maybe not. Okay, let's try again. Unhandled. Local variable invoke count reference before assignment. Okay, that's a scoping thing in Python. I think we have to say global invoke count. Let's try that. Okay, invocation count 1, cool. Invocation count 2, 3, 4, 5. As you can see, this number is going up. And so that means it's reusing this invocation context, this Lambda kind of micro VM invocation context. So, however, if I was to execute 2 of these at once, one of them would say 1 and the other would say 6. Because it would have to start up a new context, I think. I can't hit this button that fast, but you get the idea. And if I was to hit this again in, say, 20 minutes, it would probably say 1 again, because it would go to sleep. Any questions on that so far?
Yeah. What would happen if I try to spawn a thread while a handler is running?
If you try to spawn a thread while a handler is running, so there's nothing wrong with spawning threads inside your function. You can even leave the thread running, I think. There's nothing to stop you from spawning a thread inside the function. However, you probably want to make sure the thread finishes before the function finishes. You have no guarantee that anything that's still running after your function returns will not be killed by Amazon. It would not be safe to leave a thread running. If you can, I don't know if you can. You can definitely run a thread and join it inside while your function is being executed. Nothing wrong with that at all. But Amazon says pretty specifically, like I was reading about their execution context here. So here it says, background processes are callbacks initiated by your Lambda function that did not complete when the function ended, resume, which is kind of a weird phrase. If AWS Lambda chooses to reuse the execution context, you should make sure any background processor callbacks are complete before the code exits. So it says, when you write your function code, do not assume that Lambda automatically reuses the execution context for subsequent function invocations. Yeah, they're saying don't expect anything to persist. So like what I'm doing here, by creating this variable, this is not safe. This is not a good practice. This could go away anytime. There's no guarantee about it at all, other than this has been run before, this is executed, but that's all.
I can see one application that would be safe. We could use this global global variable as a cache.
Yep.
Let's say that Lambda has to download something from internet. We can just, every time we use it, we can check if it's still in the context, if it's defined. If not, then don't load it. But if it is, use the cached version.
Yeah, absolutely. Can use it as a cache. There's use it to memorize functions. Sure. An example they give is database connections as well. They say like, you know, you could, if your function establishes a database connection, reuse the original connection in subsequent invocations, stuff like that. So yeah, that's, as long as you don't expect it to always be around, you should be okay to persist stuff. And you also get 512 mega RAM and /temp if you need that. Maybe you're wondering, how does this connect to the web? How are we getting, where does HTTP come into this? Maybe you're not wondering that, but that's what we're primarily using Lambda for right now. So let's dig into that a bit. So Lambda is, again, the API is very simple. The API just lets you create a function and invoke it and do some, you know, basic management tasks and layers and things. But basically at the core, that's all it is. Now, there's different ways to invoke it, and Amazon can invoke it on your behalf in lots of different ways. And we can see here, it has a little picture. So you can have triggers and destinations. It's a nice little GUI here. And these are some of the things, well, these are all the things, I guess, that can trigger your Lambda. The main ones, API gateway, which we'll talk about. This is to invoke it when a request is made via HTTP. Alexa, load balancer, CloudWatch events, things like alarms, like if you trigger an alarm on something like you know, CPU is too high on some instance, you can invoke a Lambda. Logs, Git, authentication, DynamoDB, like stuff changes in a database. This is for streaming data. S3, you know, if you say put an object in a bucket, you can invoke a Lambda, stuff like that. SNS and SQS for kind of message queues. Different ways you can invoke. And of course, you can do just a direct API call. So for internal services that we use, there's no necessarily requirement that we invoke them via HTTP. So for example, for the scraping stuff we're doing, as one example, we don't have to send the results from the scraping back through an HTTP API. We could just call a Lambda function directly and say, you know, hey, here's the results. Here's what I scraped. So if we have services calling other services, as we do in some applications, again, it doesn't have to go through HTTP. We can just call it directly through the invoke API call. But let's look at API gateway, because it's pretty interesting. So remember, if we have stuff coming in from the internet, like let's say we want to make a REST API, we generally put API gateway in front. So API gateway is a wonderful service from Amazon. Has nothing to do with Lambda. All it does is basically give you a way to process HTTP requests. It can do SSL and JWT, WebSockets, a lot of stuff. These are the different kinds of APIs you can create these days. It used to be they only had REST API. Now they have 4. You can do WebSockets. This is new. This is new as of last year, this year. REST API is kind of classic. HTTP is a little bit more kind of specialized. You can't do everything that you would do with the REST API, but this does have support for more common helpful things like cores and JWT. So I haven't really worked too much with HTTP API yet, but hey, no time like the present. So let's make a API. Let's call it like demo API.
So, Mischa,
Yeah.
one question. Do you ever use web application for that? For commercial applications, we just write it in code, right? Because I haven't seen these screens before. This is just for presentation, right? But when we do it like for the client, we use infrastructure as code or serverless configuration.
Exactly. Yeah. So I'm going through the basics, like if we're doing everything from scratch. But yes, that's right. Serverless automatically creates the API gateway resources for us. So you've probably all seen this. You probably all know what this looks like. Let's see. It looks something like this. Or actually, we usually say like proxy here, but it's the same idea. We say, okay, this function is triggered by a HTTP event. And when you specify this in serverless YAML, this will create an API gateway resource for you. We don't normally interact directly with API gateway because serverless creates it for us. But let's do the basics here so we understand what serverless is actually automating for us. Okay, so routes. Let's see. Okay, we need to say connect to Lambda. So this is what ties the URL to your Lambda function. So we can go here, we can type in hello demo. This is the format of the invocation, the format of the event that our function gets. 2 is new. This came with the new HTTP API. Most of the stuff we're using, I think, uses 1.0. Yeah, this is more for new APIs, like if you want to use the OAuth stuff and whatnot. So this is basically what's connecting API gateway to Lambda. So we can go ahead and add a route. We can say like, maybe get hello, and then we say call hello demo. Cool. And create. Now, if we go back to our Lambda here, we'll see something in the picture. Let me reload. We should see API gateway now in the designer here. So we can see that our function can be invoked via API gateway. And we can add other triggers if we want. Cool. So API gateway, here is our invoke URL. And if we want, we can go ahead and call it. So now I can actually call our function. Instead of just doing invoke directly as an API call, I can also curl it. Cool, there it is. Working exactly the same. Same function, haven't made any changes to the function, but now I can call it via HTTP.
Maybe reserved concurrency and throttling would be interesting to hear about.
Okay, sure. So reserved concurrency and throttling. So there's a lot of reasons why Lambda is cool. And but one is that you get auto scaling for free. So this is something that used to be a huge challenge, used to be hard and or expensive or both. If you wanted to scale up or down based on how much traffic you were getting, you had to start up virtual machines, or even some places will rack buy new machines and plug them in or whatever. But with Lambda, because Lambda puts so many constraints on our application. There's so many things it can't do. There's so many things that using Lambda prevents us from doing. We can't run longer than 15 minutes. We can't write more than 512 megabytes to the disk. We can't go above, I don't know, 2 or 3 gigabytes of RAM, blah, blah, blah. All these restrictions, all these constraints. But in return for us making these sacrifices, we get a lot of cool stuff in return. One of the cool things is, because our functions are lightweight, relatively speaking, compared to starting up GUnicorn or something, Amazon can just run them wherever it wants, and it can start it up, and it can kill it at any time. It can put them wherever on whatever machines it wants, and we can basically auto scale. So no matter how many requests come in, Amazon can theoretically probably process all those requests simultaneously by just creating hundreds or thousands of copies of our code and running them. That's pretty cool. That means we don't have to worry if we get a sudden spike in traffic. We can scale up and scale down, and we pay for just what we're using. We don't have to really pay to have servers running that aren't running at full capacity all the time. So, that's one of the problems with kind of traditional hosting of web applications and other servers. You have to buy hardware or, rent hardware. And you're probably not using, if you have 100 web servers, you're probably not maxing out the CPU and the RAM and the disk and the network and the power consumption of all those machines all the time. You probably have that much, so if you get a big spike in traffic, you can handle it. But the rest of the time, they're probably at least partly idle. But you're still paying for that idle capacity, even if you're not using it. With Lambda, you really are paying by the gigabyte second, 100 mil, whatever. You're paying for what you're using in terms of RAM and CPU time. And that's pretty cool. However, there are limits, of course, as with anything in life. So that's under the concurrency section here. So by default, I think you get 1,000 maximum concurrency of 1,000 invocations. And if I remember correctly, this is across your whole Amazon account. So you can only have like 1,000 functions running simultaneously on your account. And if you want to see what the limits are, we can Google Amazon Lambda limits. We can see here exactly what those are. And they vary by region, but it's usually like 1 to 3,000 or something. So these are important. These are definitely something that are worth keeping in mind when working on Lambda, when using Lambda. We're limited to 75 gigs of function layer storage, 1,000 concurrent executions, 3 gigs of RAM, 15 minutes, 4K of environment variables, all this stuff. Payload is also interesting. So the biggest invocation payload can be 6 megabytes. So you can raise these to something. You can request to increase. I don't know what the hard limit is, but by default it's 1,000. And you can make it lower. You can say only run one of these at a time, or only run, I want to have three reserved at any time. And I think that means that there's a couple different components to this. One is how many functions you want hot, like ready to serve requests. So if you have a high startup time and you're willing to trade off money for availability, for like getting rid of that cold start time, you can. But there's also a limit of how many of this function can run it at once. But I think that's a different setting. I'm not sure what that is. But what will happen is, let's say I reserve concurrency of 1 here. If I want to hit this, let's see, let's do a little live experiment, shall we? Before we return, let's do time.sleep. Say 1 second. So if let's have an unreserved amount concurrency. So right now, if I hit it twice in 1 second, it should spawn 2 different functions. So let's do this twice. So I can just do this, I think. Now see, they both returned 1 invocation count. Now if I do it again, we got 2, 2, 3. Can kind of reason about what's going on here. It's running some of these in parallel. So if I set this to reserve 1, again, I forget if this is the setting for keeping it hot or if it's for limiting it to only 1 at a time. I think this limits it to 1 at a time. So if I do these, I actually get service unavailable. Instead of starting up a new function, it just says, oh, sorry, can't process anymore. This is useful because sometimes maybe you only want to have one thing running. So in our task executor, we have something that's like pulling off tasks off the table and working on them. And the thing that's grabbing the tasks and then running, executing them, you only really need one of those running at a time. So this is a useful limit for that. Or, maybe set it to something low. If you have a function that takes, some time to run, maybe you don't accidentally want to invoke 1,000 of them at once. If you do that for a while, you'll get a pretty big bill, probably. So, if you could accidentally invoke 10 million lambdas all at once, you would rack up a big bill pretty fast. So that's part of the reason for this limit, I think. let's do one more thing I was playing with today. So as mentioned before, there's some different runtimes that come with Lambda that you can use that are ready to go. I think they're all open source. I think you can go look at the source for the Python 3.8 Lambda. I'm not going to try and find it right now. But they're relatively straightforward. It's what you would expect. It's like, import, and then, call the function, and capture standard input and output. And, that's probably all. It's not doing that much. But it does kind of manage the dependencies and importing your code and all that. But you can create a custom runtime. You aren't limited to just these things. So I was playing around doing that. It's actually not too complicated. There's a tutorial here I was going through. Maybe we can check it out real quick. So the way it works is a Lambda function with a custom runtime has a file called bootstrap. And this should be an executable file, and I think it's run. It's just execed, I think, by Lambda itself. It has some environment variables set. So you have like this Lambda task root, which is a directory containing like your deployment package, and then AWS Lambda runtime API. And this is a like IP address. When your handler is called for your function, there's this, it hits this endpoint, and this endpoint contains, I think, the payload and information about the current invocation. The HTTP request will block until one is received. So this is actually sitting here in a loop asking for the next invocation. And then that invocation, this URL will contain some data about the invocation, like the payload and the context. And then when you're done, you post to request ID response like this. So that's actually how Lambda works under the hood, the runtimes. It's pretty cool. If you want to implement your own Lambda runtime, all you really have to do is read in, Lambda task root if there's any files you need to access. Hit this API. It's just JSON, it's just the JSON REST API like everything else. And then post the response. That's it. So this was implemented using Bash, because why not? Got this bootstrap thing. So this is actually kind of fancy. What it does is it loads handler. So I think this underscore handler is the name of the handler that we configure. So we can go ahead and create this runtime if we want. It's pretty straightforward. It looks like create. No, one sec. This is what the function, the API call would look like. So call Lambda create function. We name it bash runtime. I already did this, but it's the same thing. We give it a zip file. So when you create a function or update a function, you give it a zip file. The zip file can be, if you're using this command line client, you can just pass it in. But usually it's a URL, it's a S3 URL to a zip file. That's how serverless works. When it packages up your function and deploys it, it actually makes a zip file, uploads it to S3, and then calls create function or update function with a S3 path to your zip file. And the zip file, by the way, we can make that. It just looks like this. It's a zip file that contains two files, function.sh and bootstrap. And function.sh looks like this. Is called with event and context. Like, we're used to seeing in Python, like, def handler, event, context, So we create a zip file. We say our handler is going to be called function.handler. And then runtime provided. And then we give it the execution role to run as. So this creates a Lambda function. I don't know if we can look inside of it, but it should appear here. Here, let's take a look. So this is the contents of our zip file. So we can see here's our bash code in our function. Handler is set to function.handler. So this, I believe, is this environment variable. And so this says cut at the dot. So delete everything and then grab the first field. So that means basically split this string on dot and grab the first part of it. Here, what it's basically doing is it's saying load lambda task root / function.sh. So it's really saying, okay, source this function. So now we have a function called handler in this script. I don't know if you guys are too familiar with shell scripting, but this is basically just saying include this file. That's all. That's all this is doing. And then we make a temp file. So this creates a temp file in /temp, and then we say use curl and call a get on runtime API, runtime invocation next. This will give us back some data about what we want to process. I think it sticks it in this file or something. It's not really important, but basically then it just calls handler split second field. So that's saying call this part of it. So it loads a file called function.sh, and then here it's calling a function called handler. So it's really, really, I don't know what the word is, jankety, ghetto. But it's basically doing the same thing our Python runtime does. It says, okay, import this file, and then call a function inside of it. And then post the response here with curl again. That's really it. And we can invoke it like any other function. Let's see what happens. We can see it's echoing our request. So this is coming from function.sh. So it's saying echoing request event data. And that event data here, this is, of course, what we sent in our test. If you saw that, yeah. This junk here, hello, JSON. Run it again, there it is, hello. So this is all custom runtime, just using bash. Doesn't have to be bash. We could run WebAssembly, we could run Rust. I mean, well, for those runtimes, I mean, you can just run a binary application. There's nothing that says it has to be a scripting language. We could upload any binary that's compiled for Linux x86 64 architecture and run it. Yeah, it doesn't have to be interpreted or anything like that. And then we can make a layer out of it. So if we want a reusable runtime, we just attach that layer. And when it executes your Lambda, if your Lambda doesn't have a runtime, it'll look to see if there's a program called bootstrap. If that doesn't exist, it'll look through all the layers and see if any of them have a bootstrap file. And if it does, then they'll run that. It's kind of like booting a computer. You know, it's looking through the different volumes to see if any of them have a boot signature. Yes, Jan, you are raising your hand.
Cool. Yeah. Can you tell us more about Lambda layers? How does it work?
Lambda layers are these guys here, and they're kind of reusable file systems, I think, is how I understand it, that you can attach to a layer. So we can make a layer out of this. So you can use it to make a runtime. So like I was just saying, if you have a layer that has this magic file in it, an executable bootstrap, and you don't have a runtime set on the function, and the function doesn't contain this file, it'll use bootstrap from that layer. But you can use them for other things as well, not just runtimes. You can, a layer, the way it seems to work to me is it's a file system overlay. So you could create a layer, you could create like, you know, like layer slash.
Can you show us this Postgres layer that we have already, that which already provides?
Yeah, we have a number of layers that we make. And all they really do, I mean, we can look at it. This is, I think, the script to create the layer. In effect, let's see. In effect, one second. Layer psycho pg2 3.8. You just create a folder. Like, it's just a file system, really. It's just a collection of files. So we have this folder, and you can think of anything inside of this as like slash. So layer slash Python psychopg2. This is what the layer looks like inside. It looks like there's a directory called /python. Inside is a directory called psychopg2. This is like the root of the layer here. So then when our Lambda application runs, these files appear on the file system. They get merged in. It's an overlay. So I could be wrong about this. I haven't actually read documentation that says exactly this, but based on how layers are constructed, this is my understanding. If you have a layer that looks like this, /python/psychopg2, when your Lambda runs, there will be this directory, /python/psychopg2, like at the root of the file system. And I believe the Python runtime looks for dependencies in /python. And so by putting this directory in there, we are saying, okay, if you do import psychopg2, then it'll search Python path. So you can think of it as Python path will be like /python in the Lambda runtime environment. So when you say import psychopg2, it looks in this directory and others. And if it sees a directory named psychopg2, then I can import, psychopg2.errors.whatever, or psychopg2.foo if it's in init.py.
That's cool.
One of the reasons we need to make this a layer is because of this file here. Psychopg2 is linked. It uses FFI, foreign function interface. It's linked against a shared library. It's linked against a library of code that is not Python. It's like, an executable library. It's a binary. It's this thing here. If I try to run this on my Mac, I can't, because this is for GNU Linux. It's a different format. If I try to run this, it'll tell me like, no, fuck off. But because Lambda is like I was saying, x86-64 Linux, this code can be executed on Lambda, but I can't really build it on a Mac, so we use Docker to spit this out. It basically, the layer script says, okay, build this, and then spit it out in the Docker container, and then it copies it from the Docker container into layer /Python. So you can use this to create reusable dependencies or runtimes, and they can include native code. That's the point of layers. You can have a max of 5 layers. We have one we're using in some new projects that maybe a simpler one to look at is JetKit. JetKit provides everything except JetKit. The idea here is, let me see, Docker file. Again, we're using Docker, and we use the Lambda continuous improvement called lambda Docker image as kind of the base to build stuff on. This is pretty close to the runtime environment. So if you want to play around in the Lambda Python runtime environment, you can. You can just say like Docker run pi build Python 3.8, I think. And you can be in an environment that's very, very, very similar to what your execution environment is on Lambda. And so we use that for building stuff. And we just say run pip3, pip3.8, install, Flask, SQL Alchemy, PyTest, Alembic, all this good stuff. And then in some of our new projects, you'll see that these are not included there. I forget if it's in here. Let's see. Yeah. So here you can see no deploy. These are all the Python packages that are built by this guy and their dependencies. And so we say, yeah, you don't need to upload these. They're provided by the layer. So this makes our package go from, what's the base size of our deployment? I don't know, 8 megabytes or something, down to about 1 megabyte. Because the layer is already uploaded, it already has all these files, so we don't actually need to provide them. So
it's just so the packages are smaller and the deploy time is also smaller. Right?
Yep, exactly.
And what if you want to bump version of package?
So every layer is versioned. So when we include a layer, you'll see here at the end This is the ARN. So blah, blah, blah. Layer jetkit Python 3.8:3. So this is, we're saying we're using version 3. So if we make a new version, everything still sees the old layers unless you manually go in and increment it here.
Cool, thank you.